Muy buenas tardes con todos los presentes. Continuando con la programación del quinto Congreso Internacional de Topología y Afines, tengo el agrado de presentar al doctor Matheus Duzi Ferreira Costa. Muy buenas tardes, doctor Matheus.
Buenas tardes. I first apologize because my Spanish, I can understand Spanish quite well, but my speaking Spanish is more like a Portuñol than anything else. So I'll spare all of you and I'll give my talk on English. I hope that's okay. Is that okay?
Ok, ok. Voy a presentarlo, ¿sí? Lo voy a presentar.
Right.
Bien, él es licenciado en física por el Instituto de Física de San Carlos, la Universidad de Sao Paulo. Posee una maestría y un doctorado en matemáticas por el Instituto de Ciencias Matemáticas y Computacionales de la Universidad de Sao Paulo. Cuenta con experiencia en las áreas de física y matemáticas, con una especialización en análisis, topología y teoría de categorías. Trabajó como profesor contratado en el Instituto de Ciencias Matemáticas y Computacionales de la Universidad de Sao Paulo y actualmente es investigador postdoctoral en dicho instituto. Muy bien, él nos presentará su ponencia titulada The Thin Line Between Edge Direction and Edge Length Spaces. Espero haberlo pronunciado bien. Adelante, doctor.
Muchas gracias. So I'll continue. After this introduction, my talk, I opted for this style of talk because I think this is a kind of subject which benefits. Are you hearing me well? Can you understand me well?
¿Se escucha? Sí se escucha.
Okay, great.
Yes.
So I think this kind of subject benefits from a lot of sketches and drawings. So I opted for this kind of presentation here. Okay, so I expect to give a somewhat basic talk. I'm gonna go into a bit more into details of what Gustavo presented on, I believe it was Tuesday. This is a joint work with Gustavo and Paulo from the institute I'm from. So let us begin. Oh, so let's start with graph theory's basics, because we're going to talk about topology and graph theory here. So I'm going to consider a graph a pair where V and E, where V is a set, which we're going to call the set of vertices of the graph, and E is a set of unordered pairs of vertices. So V is the set of vertices, E is the set of edges. So I said I was going to use a lot of drawing. So I'm going to denote I'm going to draw the vertices of a graph as these dots on screen that you can see on screen on white. And the edges are going to be connecting lines between the vertices in the graph. Okay, so these are the unordered pairs. Fine. A G path is going to be a finite sequence of vertices, a finite sequence which does not repeat any vertex, and such that two subsequent vertices in this sequence always have an edge between them. So right here, So right here, I denoted an example of a sequence in the graph that I previously sketched. Right? So it's a sequence which starts with this vertex, then goes to this vertex, and this vertex. This is a sequence because it does not repeat any vertex, and because any subsequent vertices have an edge between them in this graph. What wouldn't be a path would be if, for instance, the third vertex would be, for instance, the the same as the 0th vertex because it would repeat a vertex, or if the third vertex was, for instance, these vertex right here, because this vertex does not have an edge with this vertex right here. So that wouldn't be a path. Okay. So what is going to be a ray in a graph, a G ray, is going to be essentially an infinite path, right? So it's going to be an infinite sequence of vertices, which also does not repeat any vertex, and which also has the property that two subsequent vertices in the sequence have an edge between them. So again, I write here, I give here an illustration of that. So on a graph, I illustrated the ray which starts with this vertex, then goes to this vertex, then goes to this, and this, and this. And in here, I did something that I'm going to do throughout all of this talk, which is I'm going to denote, well, rays are, as he was defined, they are infinite sequences, right? So in order to denote the infinity of the sequence, I'm going to use this arrow notation. This arrow means that the sequence continues infinitely in that direction, so to speak. Okay, so this is an example of array on a graph. Obviously, because array is an infinite sequence of non-repeating vertices, it follows that in order for a graph to have array, the graph must be infinite, right? Particularly. So another technical terminology here is that if we start with array as an infinite sequence, which is array, then if we consider the same sequence but from a certain point onward, from a certain point onward, then we're going to say that this is a tail of the original ray. Okay, so we're going to say that a set of vertices of the graph is connected if for each pair of vertices in this set H, there is going to be a path between the two vertices. So, for example, in the graph that I draw in the beginning, we can see here a set of vertices, H and H, whose set of vertices is connected, right? Because between any pair of vertices in here, I can come up with a path between them. If, on the other hand, I chose H or the whole G, every vertex in here, that would not be connected because this vertex it has no path between it and any other vertex in the graph, right? So that wouldn't be connected. So this is all of this is graph theory 101, right? I'm sure a lot of you are already familiar with this, so I'm not going to go into many details on it. Let's at last talk about ends of an infinite graph. So that's a word that appears in the title of the talk. So in order to talk about ends, we need to talk about equivalence between rays in a graph. So we're going to say that two rays are equivalent if whenever I pick a finite set of vertices and I take it away from the graph, the tails of the original rays are going to lie in the same connected components of the resulting G set minus F, right? So with examples, here we have an example, a simple example. So we have denoted here one ray here on top and what we call a double ray below. That is a ray which goes to the right and a ray which goes to the left. And in here, I use the 3 dots to denote that this pattern of vertices connecting from the top ray to the bottom ray continues infinitely. Okay. And in this case, what's happening here is that the top ray to the right, that goes to the right, is equivalent to the bottom ray, which goes to the right as well, because they are infinitely connected. No matter how many, finitely many vertices I take away from the graph, the tails of these two rays are always going to be in the same connected component. So they are equivalent, right? However, as my illustration here clearly indicates, the ray to the left is not equivalent to any of the rays that go to the right, because if I take away, for instance, these finite set of vertices, which are circulated here, I will completely separate. This ray will be in a connected component of the graph, of the resulting graph, and these are going to be on another connected component of the same graph. So they are not equivalent. I found the finite set which separates them completely. Okay. So this is the notion of equivalence between rays. We're going to say that the collection of equivalent classes, of these equivalent classes, is going to be the set of ends of the graph, right? So each equivalent class, by this equivalence relation that I've just defined, each equivalence class is going to be an end of the graph. So examples. Here I already indicated an example, right? We have an end which is represented by the ray which goes to the left. Let's call it epsilon L from left. And we have another which goes to the right. Let's call it epsilon R. Of course, we have many different rays. We have a ray which goes up and down, up and down. These are all equivalent. This is a simple exercise to check, right? We have many rays here. The claim is that we only have these two equivalence classes. Anyhow. So, all right, this is an example. Another example is what we call the star of rays, so to speak, the infinite star of rays, in which, in here, what I mean by this, we have a vertex, a centering vertex, from which countably many rays emerge, right? And all of these rays only connect on this vertex. In particular, it should be clear that if I remove this single vertex, I will have each of these rays on a different connected component of the resulting graph, meaning that all of these rays are not equivalent to one another. They represent a different equivalence class, right? A different end of our space. So we have infinitely countably many vertex ends in this graph right here, which is going to be a particular important example later on in the talk. And another example which is going to be important later in the talk is the next one, which is we have a distinguished top ray and a distinguished bottom ray, and we have a vertex in the middle which connects to which has an edge to every vertex from the bottom ray, and it has an edge from every vertex from the top ray, right? Now, it should be clear. This example is kind of silly right now, but next it will be clear. It will be clear why it is important. But at the moment, it should be clear that we have two equivalent classes here. If I remove this vertex, we'll have the top ray in one connected component and the bottom ray in another connected component. So they are not equivalent, right? And these are indeed it is easy to check that these are the only equivalence classes in this graph. All right. Now, given an end on a graph and the finite set of vertices of this graph, we're going to consider the following set of ends. So this is a set of ends. This is contained in here, right? It is going to be the set of those ends for which their tails, the tails of their rays, are in the same connected components of G set minus F has the connected components of the epsilon that we started. Okay, so I'm going to fix an epsilon. I'm going to fix a finite set of vertices. I'm going to look at every possible end whose rays lie in the same connected component as the rays of epsilon. Okay, so with this, we can consider omega of G has a topological space in which whose topology is generated by these basic sets. So this forms a basis, a topological basis. And we consider it as a basis to form what we call the end space. So we're going to call this the end space. Right. If we look back at the examples that I just gave, well, actually, they are not all that interesting because they are all discrete. Right. In this particular cases, they're all discrete. However, if we look at another more interesting example, such the infinite comb of rays, because it looks like a comb, right? So in this example, we have, again, for each of these of the upward rays, we have a different end. Each upward ray represents a different end. Why? Because, well, for instance, for this ray, if I remove this vertex, it will be isolated. If I remove this vertex, this will be isolated. If I remove this, this will be isolated. However, I can never isolate this ray from all of the upward rays. I can always separate it from any given ray, upward ray. I can always separate. If you give me an upward ray, I can separate this horizontal ray from it, but I can never separate it from all of the upward rays at the same time, right? And it is a simple exercise to check that with the aforementioned topology, this is the space of the convergence sequence, right? So we have a sequence of points, and in the topology that we have just defined, this sequence of points will converge to this point in the space, right? So this is homeomorphic to the space of the converging sequence. Okay, now moving on to another topic from the title of the talk, directions. So a direction of a graph G is a function f which selects for each finite set of vertices a connected component of G set minus f. But f cannot choose the connected component randomly. It has to have some coherence, and that coherence is illustrated by this property. So if I have a finite set f1 which is contained in a finite set f2, then the component chosen by f for f1 will contain the component which is chosen by f for f2. Okay, so this is a coherence in the direction. We're going to denote D of G has the set of all directions of G. And examples here, I'm not going to go into many technical examples because I'm going to go straight to a very big result in the field. to give you an idea of this result, let epsilon be an end of the end space of the graph. Then we can actually use epsilon to define a direction of G in the following way. For each finite set, for each F finite set of vertices, I'm gonna make F epsilon choose the connected component of G set minus F, which contains the ray of epsilon. You can always do that. And in this way, this function will be coherent in the way that we want, and thus you will define a direction of the graph. And in fact, what is somewhat surprising, perhaps, is a theorem which was proved by Distel and Kuhn, which states that this association, which takes an end of the space and from it constructs a direction of the graph, is actually a bijection between the end space and the set of directions. So this is actually a bijection. What is most surprising here, actually, and it is in fact the hardest part of the proof of this theorem, is to show that this is surjective, that every direction can be constructed from an end. This is the hardest part of the proof. All right. Let me just keep the time here so I don't extend myself. All right. Now we're going to tell a similar story, but now with edges as the protagonist. How so? Well, here I have just copied and pasted the definition of for the ends of a graph, for the equivalence relation of the graph, of the rays in the graph, and anyway, this is the definition that I have previously presented to you. This is something you've already seen in this talk. Now, what I'm gonna do, I'm gonna note that in here I made the choice of separating rays by finite sets of vertices. What I'm gonna do now is simply separate the rays by finite sets of edges. So I'm gonna say that two rays are going to be edge equivalent if for every finite set of edges of the graph, the tails of R1 and R2 are in the same connected component of G minus F. Where here I'm considering the graph G, where I take away the sets of F from G. I erase them. And we're gonna say that the collection of such equivalence classes is the set of edge ends of G, and we're gonna denote it by omega E of G. As for the topology, here I have the definition of the basic open sets and the topology of the end space. And in here, once again, we had chosen to use finite set of vertices. Now what we're gonna do is simply switch it for considering finite sets of edges, right? So a basic open set associated to a finite set of edges of an end epsilon is going to be the set of all ends whose rays lie in the same connected component of G minus F has the end epsilon. And we're going to consider this has the edge end space, the space, the topological space whose topology is generated by these basic open sets. And here again, I copied and pasted the definition of a direction of the space, a direction of a graph. Once again, I note here that we chose the choice functions are, they choose connected components of G minus set minus F when F is a set of vertices. Now we're going to consider edge directions, choice functions for sets of edges. And in here, I must note something important. We want to ask for an infinite connected component. For directions by vertices, the original, the definition, it is easy to check that a direction, a function which is a direction, will always choose an infinite connected component. It always has to choose an infinite connected component, because if it were to choose a finite connected component, then I could choose. How would it choose? If I pick the finite set has the finite connected component that it chooses, then it wouldn't have anything else to choose afterward. So it always it happens to always choose an infinite connected component. In here we have to ask it. But anyway, it's the same story, except we trade vertices for edges. Now the examples. It looks like we have the same examples here. And in fact, for these two, we have the same scenario. The equivalent classes by edges are the same as the equivalent classes by vertices. However, in this case below, recall that we had two equivalent classes. We had the equivalent class of the ray above, and we had the equivalence class of the ray below. But now we have a singular equivalence class. Why? Because I can no longer pick this vertex to separate the two. I can only pick a finite set of edges, and for any finite set of edges that I pick, there will always be other edges which connect the ray above to the ray below, right? So I can never separate the two rays by edges, by finite edges. So in this case, the edge and space is different, clearly different. And I put here a result from Aurique, Magalhães, and Real, in which they showed that for every graph G, there is actually a graph HG such that the edge and space of G is homeomorphic to the classical usual end space of H of G. So an edge end space is always realized by a usual end space. However, in the same paper, they show an example of a usual end space which cannot be realized by an edge end space. So in particular, I'm not going to go into many details, but this is a graph obtained by, you take the binary tree, and on top of each of the branches of the tree, I plug an extra ray, and I connect it to the vertices below in such a way that everything works. I'm not going to go into many details. This is the Alexandrov duplicate over the binary tree, and this is the counter example. Nevertheless, to summarize these two results tell us a story. And what is this story? It tells us that if we consider the class, and here I am considering this is has the class of topological spaces which are realized by regular end spaces of some graph, right? And below we have the class of all topological spaces which can be realized as the edge end spaces of some graph. What these two what the previous theorem and the counterexample that I just presented to you tells us is that these two classes are two different subclasses. This class is a proper subclass of this class. Right. And now it is only natural to ask, what about the edge directions, right? Where does it fit in here? So this is what we set out to answer in our paper. Indeed, a few things quite different happen when we consider edge directions. For instance, recall the result from Distal and Kuhn that every direction can be constructed from an end of the space, right? Can be represented by an end of the space. The same thing, however, does not happen for edge directions. It is not the case that every edge direction can be represented by an edge end. And this is the example. This is I told you that the infinite star of rays was going to be important as an illustration. Why? Because, okay, every one of these ends, these are still the edge ends of the space, and they still define edge directions in the same way that regular ends defined regular directions. However, now we have an extra direction which is not realized by any edge end, which is the edge direction defined by this vertex right here. So consider the direction which, for every finite set of edges, picks the connected component which contains this vertex. It is a simple exercise to show that this indeed defines an edge direction. These connected components which contain this vertex V are always going to be infinite indeed. So it is going to define an edge direction. And thus, this is an example where the representation, an analog of the representation theorem from Distal and Kuhn does not work. And in fact, what we had shown is that for every graph G, there is a canonical embedding. The canonical embedding is the association defined by Distal and Kuhn. There's no mystery here. Given an edge end, we define the edge direction in the same way that Distal and Kuhn did in their paper. But furthermore, if G is a connected graph, then this embedding is closed if and only if the edge end space is compact. Okay. So there's this much. And this is because the edge direction space, I didn't give a topology for it, but essentially for the edge direction space, given a function f in the finite set of edges f, I'm going to consider this the basic open set containing f associated to f has every direction, every edge direction, such that G of f agrees with f of f, right? These are the basic open sets of this topology. And as it turns out, if G is connected, then this space is always compact. This is something that Gustavo briefly spoke about in his talk. So because of this fact, we have this theorem, essentially. And furthermore, for every graph, we got that, sorry, let me just, right. So for every graph, we can find a connected graph H with dense embedding from the edge end space of G to the edge direction space of H. And furthermore, for H, it holds that the edge direction space is the same as the edge end space. Okay, so in particular, if this is compact, note that this is going to be a homeomorphism. Okay. Now, finally, in the title of the talk, I said that there was a thin line between edge directions and edge end spaces. This is the line. The line is the line from the line graph. So what is the line graph? So for a graph G, we're going to denote by L of G, the line graph of G, the graph in which we're going to consider the vertices of L of G, also denoted by G prime. The vertices of this graph are going to be what were the edges of G, so the edges of G. And we're going to say that two of these edges are going to be connected in the line graph if these edges had a vertex in common. So in here I have an illustration. If I had two edges, E1 and E2 in G, and they had a vertex in common, then in G prime, in G line, we're going to have the vertex associated to E1, the vertex associated to E2, and they're going to have an edge between them. Okay, so this is the G line of a graph. And for examples, I'm going to draw out some examples. First of all, I note that if we have a singular ray, a graph G, which is a singular ray, then looking at G prime, it's going to be a singular ray as well, right? Why? Because I have these edges, right? I have these edges right here. They're going to be translated to vertices in G prime or G line. And each subsequent edge has a vertex in common, has an incident vertex in common. So they're going to be connected in G prime, right? As well. So nothing new happening here. Things start to get a little bit more interesting, on the other hand, if I consider, for instance, the star of rays, the infinite star of rays. So let's suppose this is G. And I'm going to highlight the first edge of each ray right here. Okay, so we're going to have each of these edges that I highlighted right here are going to be a vertex, a different vertex in G prime, in G line right here. From each of these edges onward, has it happened above, we're going to have a ray right here in G prime. This ray is going to be translated to this ray and so on. However, this vertex in G is common to all of these edges. And therefore, by definition of the line graph, all of these edges are going to be connected to one another. So we have what we call a complete graph right here. In particular, we have a ray down there. So a new ray emerged in G prime, a ray which did not exist originally in G, right? A ray right here, down here. And note that here we have a similarity with what happened with edge directions, because we had the start of rays, and then we had a direction associated to this vertex right here. And now in the line graph, from this vertex, we obtain a new ray down here. And of course, this is going to be the converging sequence right? You can see that this is the convergence sequence again. This is the infinite comb, except the ray below have every vertex connected to one another. And as a matter of fact, we have shown that for every graph G, that was no coincidence. The edge direction space of a graph is homeomorphic to the regular direction, to the regular end space of the line graph. And furthermore, we have shown that for every graph G, we can find a new graph G tilde such that the end space of the line graph of G is homeomorphic to the end space of the line graph of G tilde. And this G tilde can be constructed in such a way that the end space of its line graph is homeomorphic to the edge end space of itself. All right. To close the talk at last, we have also showed that the following graph has the property that its edge end space cannot be realized as the edge direction space of any graph, right? So it is it's kind of like the infinite comb of rays, except we consider these bifurcation on the comb, an infinite bifurcation on the comb. And thus, we have successfully determined with all of these results that the class of edge directions is in fact a subclass, a proper subclass. Why is it proper? Because of this example. It is a proper subclass of the class of the edge end spaces. So this is how we situate it in this diagram. And this is the paper that in which this talk is based. Essentially, this talk is based in the work that we did in this paper. It doesn't contain everything that we did in the paper. We did a whole lot more. We characterized compacity of these of some of these spaces, for instance. But yeah, this is where I base my talk, and that's it. Gracias.
Ok. Muchas gracias, doctor Ferreira. Muy interesante su ponencia. Vamos a pasar, si le parece, a la ronda de preguntas. ¿Alguien desea hacer alguna pregunta? ¿Alguien desea hacer alguna pregunta? Muy bien, parece que no hay preguntas, doctor Ferreira. ¿Le parece bien si vamos a presentarle su certificado? Okay.
I'll stop my presentation.
Ok, gracias. Bien. Muy bien. Voy a presentar entonces su certificado. A nombre de la Universidad Nacional Mayor de San Marcos, se le otorga el certificado en calidad de ponente en el 5º Congreso Internacional de Topología y Afines. Muchas gracias, doctor Ferreira, nuevamente. Muchas gracias. Thank you very much.
Muchas gracias.
Okay.